Hi there. Yeah, when I design a system using the STM32 microcontroller, I like to make a thing called a busy box. So what I do is I take the main card and I interface it with the different sensors and motors, and what I do is I work a lot on quadcopters and different embedded control systems. So I like to make a little prototype system first before I put it in a system I'm going to design to test out. So what I have here, I have the STM32 Discovery Board with a bunch of modules, and I'm going to go through the operation of each module, and I want to go through how I got there, what steps I had to go through to implement the software. So I'm using CubeMX and the IAR compiler. I'm using the hobbyist version, which is limited to 32K, and I'm just a hobbyist here, so I'm just experimenting and playing around with microcontrollers. I don't make any money off of this. It's just for fun. So what I have here is the IAR Embedded Workshop, and you can see Live Watch running here. I have a thing called a frame counter. So this system, I have a 500 hertz update rate on the system. I have a timer, and it's set up when it runs out. It sets the interrupt, which sets the frame rate. And so this one, I'm not using a real-time operating system with this. I'm just using interrupts. Sometimes I use a real-time operating system, but for this system, I'm not doing that. So anyway, I'm going to go through each module and how it works and what it does, and show you how that works. So the first module I got here is called the MPU9250, and it's a 9 degree of freedom inertial navigation type system. It gives you 3 rate gyro signals, 3 accelerations, and 3 magnetic directions. And so this has an I2C interface that I have connected. And I'm going to move it around, and we'll take a look at some of the data that it generates. So I'm holding the MPU9250 inertial sensor still pretty level. So you could see that the Z acceleration is reading minus 32 feet per second squared. If I turn that upside down, it should go to negative minus 32 feet. So I turned it upside down, and that's approximately negative gravity. And I'm going to turn it back up again. Here, let me pull this back a little so we could see the data a little better. Okay, so now I'm going to do the y-axis, well, x-axis gyro. Okay, so I'm going to move it one way. So you could see it went to about 55 degrees per second. Now I'm going to go the other way, and I went to minus 30 something degrees per second. So we're going to do it in the y direction one way. So I'm getting about minus 9-10 degrees a second. I'm going to turn it the other way, and I get 15 degrees a second. Now I'm going to do the gyro in the z direction. So I'm going to rotate it, so that's 20 degrees. I'm going to turn it the other way. It's minus 30 degrees or so. So these are the compass magnetic field of the Earth. That's X, Y, and Z. And that's in micro Tesla. And also get a temperature out of this. So it's reading about close to 30 degrees centigrade. So the next thing we have is we have a brushless motor here, and we have a battery for it. And this is a switch to turn it on. And this over here is called ESC. Okay, so that's a electronic servo controller. So we could command this motor to move, and we'll do that in a second. I'll show you maybe the action of this motor. So by putting a command in, I could get this motor to move. So let's try to put a command in there. So I put a command in, and the motor spins. And now I'm going to take the command out. And it stops. So So let me show you how I put a command in. So this parameter, it's called D_PWN fix, is the command. So at 1,000 it's still, but if I put in 1100, I could get that motor. You can hear the motor running now. Hear the motor running. Now if I go back to 1,000, it stops. So I'll try that again. We'll do 1100 again. So it's moving, and you hear it moving. Now I'll try something a little bit faster, say 1120. And it goes faster now. But if I put it in 1,000, it stops. So this debugger's neat. It works both ways. You could see data coming in, but you could also stomp on memory and put in data. So another thing I have is this HC-SR04 sonar, and it measures distance. I found it doesn't work very good with quadcopters because the sound of the motor seems to throw it off. But anyway, it does work for maybe possibly other applications. And so by putting my hand in front of it and away from it, I could get the distance to vary. So we'll take a look at that next. So you can see the highlighted parameter there is the sonar pulse echo in inches. So it's reading something like 73 inches now, but I'm going to put my hand in front of it, and yeah, it's reading about 13, 14 inches now. I'm going to move my hand closer, and now it's reading 10, 9, 7, 6. I'm moving my hand closer and closer, so it's 3.4. Now I'm going to move my hand further away. So it's reading about 16 inches. Now I'll move it in closer. It's reading about 7 inches. So that works pretty good, but it doesn't work very well when with the brushless motors. So I found out how to use more of the optical sensors. The time of flight type sensors seem to work better with the quadcopters. I also have an L2 valid signal underneath it. So when that's 1, it means it's valid. It could read it's reading a good signal. It's getting a good take. But I'll move my hand away, and it will go to 0 when the data goes invalid. When it can't seem to get a good reading, but let's see. So I'm moving it real close now, and real far away. Well, seems like it's okay. So sometimes yeah, it goes invalid. Okay. So the next sensor I have here is an optical time of flight sensor. So it measures distance. Has kind of like a little laser that shoots out of it, and it's called the RFD 77402, and that's also an I2 squared sensor. So we'll take a look at that. I'll put my hand in front of it, and we'll look at the data and see how that varies. So in most cases the data is being updated at 500 Hertz. So I'm going to put my hand in front of that sensor, and right now it's reading about 2.4 inches. I'm going to move my hand away and see if we can get a change. So now it's 6.4, 7.4, 8.6, 12, 13 inches. I'm going to move it in closer. So now I got 6.85. It's kind of like what you might call a LiDAR type sensor, just a single point distance sensor. So testing that out. So the next module I have here is called the AT24C256, and what this is an I2C double EEPROM where I could store non-volatile memory. And this is just a little module. Also uses I2C, and we'll take a look at that. The demonstration I have here is that when it initializes, it starts at for the addresses, memory addresses is set to 0, and then I change them to 1, 2, 3, 4, 5, 6, 7, 8. So they're 8-bit data, 8 bits of data. They're bytes that you could store. So this is how I could test it. You could see these 4 parameters. This is memory address 0, 1, 2, and 3. Right now they're set to 1, 2, 3, 4, 5, 6, 7, 8. If I do a reset on the device, it initializes to 0 initially, and then eventually as the program runs and starts up, it'll go back to 1, 2, 3, 4, 5, 6, 7, 8. So this is a little test that I have, kind of a self-test that's built into the system. So the next little module I have is a RPM sensor. It measures the speed from the ESC, so I could get RPM. I'm trying to get the speed of the motor, and so it's a little extra card, and it basically squares up the pulses given to the ESC, so it represents RPM of the motor. So we'll test that out. Okay, so this represents the RPM. Right now the motor is not turning, but I'm going to put in this command here to get the motor to turn 1100. So you can see here the RPM is 3,533. I'm going to put a little bit higher command in there. And now the RPM is close to 5,513. Now we're going to stop it. So the RPM goes back down to some, it just stops dead at that point. Last good value. Okay, the next thing I have is a servo simulator, and by turning this knob, it simulates a servo. So the servo is like a pulse that happens every 20 milliseconds. It varies from 1 millisecond to 2 milliseconds. And that's to simulate kind of the radio control type signals that are used in quadcopters and model planes. So this parameter right here, it's called pulse seconds. Right now it's reading the 2 milliseconds, and if I turn it down, it'll go down to 1.8, 2 milliseconds, 1.7. If I turn it all the way down, it's close to 1 millisecond. So I could read the position of that knob by turning this. Sometimes it goes a high number, and at that point it's invalid, but it's done by using timers. I believe the last module I have here is the PL2303, and that takes the UART type signals like a serial output and sends it to USB. So I could read it using teraterm. So I use this for instrumentation purposes to help debug this real-time system. So the way this works is I use teraterm, and all I do is I hit a reset, and I get the data from the last session. So there it is there. So it gives me the frame count, and it gives me various data that I could select. It gives me 1,000 points that I could look at. I'd like to show you how to create the system from scratch. So I use in this case I'm using STM32 CubeMX and IAR systems, the hobbyist version. And I know there's newer ways of doing it using CubeIDE. I'm going to be looking at that pretty soon, but I'm going to do it this older way. So I have so what I do is I open up STM CubeMX. So we'll let that open up. So I'm going to make a directory here where I keep my projects, and I'm just going to make an empty directory where I keep my projects for this, and I'm going to call it let's see, here we go. I'm going to call it example 010 R3.esc. Okay, so that's where my project's going to go. So what I'm going to do is do new project, start from scratch here. And the part I have is the STM32. The part in this board is STM32F4 07 STM-F4 07 VG. So there's really only one here, but so this is it over here. So I'm going to start the project with that. So it's a 100-pin device. So the first thing I want to do is I'm just going to save the project. And I want to get to that directory that I just created. So I saved that. And just want to check that one directory, make sure that project is in there. That's anything in there now. So the first thing I like to do is just start assigning the pins. I know where all the pins are in this, so I go in and zoom in here. So my I2C is over here for the MPU 9250. So this is the I2C1 SDA, and this one over here is the I2C1 SCL. So I know over here I have a pin over here for timer 9 channel 1, and that's for the sonar system, the HCSR04. And I know I need to set the clock. So when these things are yellow, it means that not everything is set for them yet. I'm just orange when they're orange. Not everything's set, but we'll get there. So I've been using the an ADC, the ADC in the chip. Haven't assigned anything to it. And this one over here is our general purpose input output. I believe this is for that the user switch. And continue on here, keep assigning pins. So this is our ADC. Didn't assign. So PA1 is ADC1 in 1. There it goes. So we're also using the DAC. I'm just reserving it for later use. Come on, DAC. DAC out 1. DAC out 2. So this is ADC 1 in. So I multiplex ADC 1. So I believe they're 12-bit ADCs. So I want that one. I want this one over here. And this one here. And timer 1 is over here. That's for the RPM sensor to read the pulses of that. And this is the I2C for the double EEPROM. So we have an I2C double EEPROM just to store some data, and that's a AT24C256. So this is the I2C3 for our LiDAR, our time of flight sensor. And we have some timers that we use for our electronic servo controller. So I have 4 of them reserved, even though I'm only going to use one in this project that's connected. But because you need 4 if you're going to do a quadcopter. So the next thing is our UART for our PL2303. So we'll get that set up. So I'm just going through this so we can remember how to do this at a later point in time. We could watch this video, and this is mostly for me to watch in the future in case I forget how to do this. Okay, so now we have timer 12, and this is for our servo simulator. And I have some general purpose output. I just use these for to strobe. I look at it on the oscilloscope to verify that my update rate is good. This has a minor frame of 500 hertz, so pretty fast. I could get a lot of instructions, and this one is a 500 hertz update, and I'd let this one be a lower, a 20 hertz update. So I believe I have everything here. So we need to get all these things green, so we need to get everything assigned just right. We need everything set up right, but I'm trying to do it from scratch rather than copying over another file. So I just want to make sure our clock is good here. So we're going to use the internal clock, and so what we have to do is enable our high-speed clock. I believe well, this is actually an external clock that's on. It's on the board. It's on that Discovery board. So just want to check a few things down here. Let's see what we got here. So yeah, I believe that's okay. We have to go back to our clock configuration now, and I know this one. The clock that's on our board is 8 megahertz, and we're going to go through this path here. So I just want to get everything right on our clock configuration, and make sure it matched the previous system I did. But I want to show you how to do this from scratch. We're trying to get the maximum out of this clock. So this was a divide by 4. And this is 168. It's a 168 megahertz processor. So that's the fastest this processor could run. Come on, 168. And so we got that 168. We want this to be divided by 4, and this to be divided by 2. So I believe everything is good there now in our clock setup. So that's good there. So so we're going to move with this and keep on going, assigning the pins. So we're going to keep on assigning things one by one. So we have our ADC here. We could get it to come up. Let's see, so we got this. Okay. So this is our ADC here. So we have an N1, an N6, and then we have 6 ADCs. 8, 9, 10. So that looks good there. I'm gonna bring this up a little bit to make it a little bit easier. So we want independent mode, and P2 clock divided by 4, 12 bits, right alignment. So scan conversion mode, we want this enabled. So we're going to enable that. So disable, disabled, and we're going to use the DMA streams for this. And so we want the flag at the end of all conversions, and we have six ADCs here. And since we have timer 3 in this system is the frame timer, so timer 3 trigger out event, and we want to do it on both the rising and falling edge. So we have these ranks. So this is going to be channel 1, and this is going to be channel 6, and this is going to be channel 7. Sometimes you have to do this based on pins that you have available, so couldn't quite do them in order. So this is channel 8, and for rank 5 we're going to have channel 9, and for rank 6 we're going to have channel 10. So all the rest of this is good. So now we're going to do our DAC, and I believe our DAC is good. There's nothing really we need to set here. So I just want to do a save of this project. Now we want to assign our I2C1, which is used for our MPU 9250, and I believe we just want fast mode for that. So I just want to save this project. So now we want to assign our I2C2, which this one's used for a double EEPROM. So I believe we just want fast mode for that. So we'll save this. Now we want to assign our I2C3, which is used for our distance sensor. It's like a LiDAR. And likewise, we just want fast mode for that also. And all the other defaults are good for that. Now we want to start looking at our timers here. So we have timer 1. So timer 1 is used for our RPM sensor. So our clock source for that is internal, and we want that input capture direct mode for channel 1 and input capture indirect. So we're going to catch like a pulse going up and down, and I worked this out previously, the timing on this. So our prescaler is 127 for this. And our counter period is 65,535, and so I believe we just need to change this to falling edge, and this one's direct, channel 1's direct, and channel 2 is indirect. Okay. Okay, so now we want timer 3. Timer 3 is like our main timer used for our frame counter. So this is what sets our 500 hertz update rate. So we're going to use our internal clock, and channel 1 is going to be set to output compare no output, because this is like an auto reload type of timer. So our prescaler is 31, and our auto reload is 5249. So we want so our trigger event selection is a little different here. This is output compare. So let's see. So we have to change this to toggle on match. Okay, that'll get us, and I believe that's it for that one. And next one is let's see. Okay, so we got that internal clock. All these are good. So the next one should be timer 4. If we could select it. So let me do a save here. So we're trying to set our timer 4. So we want to go here, timer 4. Finally, we got timer 4 up here. So this is for our ESC. So this is let's see, this is pulse width modulation generator channel 1, pulse width modulation generator channel 2, pulse width modulator generator channel 3. If we had a quadcopter, 4 motors, that would be good for that. So we want our prescaler to be set to 99 here, and our counter period is set to 8399, and I'm going to move this up a little bit. So that's all good the way that is. So now we're going to try our timer 9, which is for the sonar. So there's our timer 9. So so we're still using the internal clock. So we want this is like reading a pulse. So we want input capture direct mode and input capture indirect. So this is our general settings for our pulse readers. So we got 65535 and no division. So the one change here, because it has a rising edge and a falling edge to be able to read a pulse. So that's good for that. So now we're going to set timer 12, which is for a servo simulator, and sometimes these take a little time to come up here. There we go, there's timer 12. So it's a similar thing, it's a pulse reader. So we want input capture direct mode, input capture indirect mode, and we want 127, and we want our 65535 here. So we have a rising edge and a falling edge. So we went the falling edge. So that looks good for there. So now we want to set our UART. And so we want asynchronous, and these settings are good for our UART. So now I'm going to go around and check different things here. So so we do have a DMA stream 2 for our ADC. So we'll go back to the ADC here. Let's go back to the ADC. So there was a DMA setting here that we want to add. Let's see. So we want ADC. So I believe this is good. We want over here. Let me just bring this out a little bit. We want our mode to be circular, and we want full words here. So I believe that's good for our DMA setting. So now we're going to look at our GPIO. I'm just going to go through that quickly. So let's see, we have our GPIO. So we have this input mode. So this one over here, yeah, this one needs a pull up on it. So we have to go pull up and a pull up one here. So if we look at our ADC, so we have our 6 ADCs here, and that all looks good. If we look at our DAC, and that looks good there. We have our I2C, and that looks good there. I2C2, and that looks good there. I2C3 looks good. RCC, so that looks good there. We have timer 1, so that looks good there. We have timer 4, and that all looks good there. And we have timer 9, that looks good there. Timer 12, looks good there. And the UART, let's see, the UART is looks pretty good there. So now we need to check our interrupt controller. So I believe the only thing we need to set here, because timer 3 is used as our main frame here, so we need, this is this global interrupt. We want to put a check here and set this to 9. So I believe that's the only change we need here for that. So one thing that's going to help me is to make a little report here that I could compare against what I did when I previously did this. So I'm going to save the project, and I'm going to generate this little report file. And so hit that, and we'll open the folder, and I'm going to compare it against the old report that I have just to see, make sure they all match. So I did do a comparison, and the report does match the old previous report I had, so we can move forward from there. So the next thing to do is to generate the code. So it's going to generate a template, and it's going to create a project for IAR Systems Embedded Workbench. So just have to hit this generate code now. So it says generating user source code. Creating the Embedded Workbench ARM project. So it's done that now, so we can open the project now. So now we're going to go from CubeMX to IAR Embedded Workbench, and this is an integrated development environment, and so we'll start populating our code. So one of the first things I do is I go into the options for the project, and this library configuration, I want to use CMSIS and use the DSP library. Okay, so for our application program, there's a user section. So the only program we need to modify is main, and this and setting up our interrupts here. So what I'm going to do is go to the previous version I did and cut and paste the code, and I'll go through that with you. So this is the code from the last one I did, and I'm going to cut and paste certain sections of this into the new build, and the important one is main C, so I'm going to open that with Notepad, and that's the only one I want to see here. And I want to also open up the interrupt part of the program, because we have one interrupt for the timer to set the frame time. So the first thing to do is I want to get user code. So the user code once you build something on CubeMX, it doesn't change the user code part. So we want to cut and paste this into our new program. So this is the includes part. So I'm going to hit copy, and I'm going to go to the project now, and I want to put it in here. So I'm going to hit paste. So just go back and check and make sure it's in there. So I'm just adding just want to add a comment here based on the previous one. So this is Rev 3 and the date's changed. And so this is let's see, Rev 3. Okay, just wanted to put a little information there and do a save. Okay, so now I want to go to the next section that has the user code. So that there's a part called user code begin PV, I guess. Right. So this is where you define all your private variables. So, oops, let me go back here again. So it starts right here. And I'm going to copy that. And I'm going to put it in the same section, which goes right in here. Okay. So CubeMX, we could kind of close that now. We don't need to deal with that unless we need to change, add something, a peripheral, add an interface. Okay, so the next section is a sheet for user code is this PFV. This is like where the functions are defined. So I'm going to copy that and going to replace that section. If I can find it here, here it goes right in here. Okay. So the next one is user code 2. So this is the part of the main process that does all the initialization. So we want to copy all that, and we'll copy that and try to find user code. It goes right in here, and I just like to go back and take a quick look to make sure yeah, it got put in there properly. Okay, so the next section is this user code and while. So there's the endless while loop that's in here. That's the repetitive part that runs over and over again, and it ends right there. Okay, I got a little extra line in there, but I'll edit that back out. So that belongs into here, and I just want to take that extra line out. So I just want to line up the parenthesis so that looks pretty good. So the way this works is an interrupt flag that the timer 3 when it runs out sets. So this part only runs when the interrupt flag is set to 1. Now at the very end it sets it to 0, so it just goes in this while loop and skips out this part until you get the interrupt with the timer, and then it restarts this again. So the last part here is this user code 4, and these are functions that are in the program. So there's only really 2 programs that you have to deal with. It's main and this interrupt program. The interrupt program doesn't have a whole lot in it. So here it is here. So that goes in there. Okay. And now we're going to save that, and now we're going to deal with the interrupt part of the code. So over here is all it has. There's this interrupt flag that I defined. So I'll copy that. And that was user code 0. So that belongs in there. And I have to find the timer 3 where I just set that parameter to 1. So it's right there. So we're going to go down here and look for timer 3. There it is right there. So we put that in there. So that's that. So now the next thing is to do our build, is try to make this, and I believe everything is connected. So I'm going to go back to the main. So the main thing is here, we're going to do download and debug. So this should hopefully make our build, and so we're going to start that off, launch that. So it's going to recompile everything, put all that code. The CubeMX made that template, and then the user code goes into main.c, and I have a little bit in the interrupt, so that services the interrupt, so when the timer runs out, it restarts the frame. So that's what sets the 500 hertz update rate. So it compiles all these other programs and links them, and these are things that now it's downloading it into the Discovery Board. So we're ready to run. We didn't have any errors. So now I'm going to attempt to run the program, and I do that by pushing this go. So we'll push that, and we'll try to see if there's any signs of life here. And so I believe the processor is running. I could tell by the lights. So the thing we want to do is bring up this live view in our debugger view. Live watch. So this has the parameters in real time that you could see. So that one of the main ones is frame counter. Frame counter. So you can see this frame counter, and that updates every 500 seconds. So I'm going to put all the rest of them in, and when I'm completed, I'll start recording again. So anyway, I got all those parameters back in, and everything's running real time. You could see everything's running. So I got back to where I was at the beginning of this video. So I was able to recreate a build, and that's what I wanted to document here in this video. So hope you like this, and this is very interesting. You could do a real-time embedded control system for very low cost. The thing that really makes this work well is the hardware floating point, DMA streams, which doesn't hold up the processor, and so those are the big things that help you. So there's a lot of things you could do with today's technology that you couldn't do just a few years ago. Well, thanks for watching this. Bye now.